In this video, we'll look at the efficiency of the Gauss elimination algorithm. After studying this video, you should be able to explain how the computational efficiency of an algorithm can be described in terms of flops, or floating point operations. You should be able to estimate the number of flops required to solve a linear system using Gauss elimination, and explain where, as in which steps of Gauss elimination is the computational cost concentrated in. So what is a flop? It stands for floating point operation, and it's a single manipulation of a floating point number by the CPU in the computer. The CPU is basically the Pentium chip that does all the calculations in a PC. A single manipulation could be an addition, subtraction, multiplication, or division is one way to look at that. One measure of the CPU performance is the number of flops, floating point operations per second, it can perform. Note this is different from the clock speed in gigahertz that's often reported in computer specs for PCs, but it is true that a fast processor, so something with a large flop count, is going to, or something with a large fast clock speed, is going to have a high flops capability. So in modern computers, addition and subtraction and multiplication and division take approximately the same amount of time, and so we can just lump them all together as flops and look at how many of these manipulations are needed in order to execute an algorithm. And counting the number of flops required by the algorithm can tell us the following. It can give us insight into where the computational cost of the algorithm is concentrated, so we can work to improve efficiency. And that's what we'll do with Gauss elimination. It also informs us how much the cost will increase as the scale of the application problem increases. For example, how much more is it to solve a 100 by 100 system? Roughly how much more time is that going to take than a 10 by 10? So we'll be able to estimate that. And lastly, it informs us how much the cost will increase with repeated executions of the algorithm. So if we want to solve that 100 by 100 system, say 1,000 times, what's that going to cost us in terms of processing time on the computer? So let's look at counting the flops required in Gauss elimination, and we're going to start with the forward elimination step, and this again is just an order of magnitude analysis. So we're just interested in how does the number of flops required to execute the algorithm depend on the size of the system. So let's go through this forward elimination step and recall it starts by starting with the first pivot element and eliminating all of the elements under that first pivot element. So if we look at the operations required to do that, recall each one will have something like row 2 is equal to row 1 minus row 2 minus A11 over A21 times row 1. So as we go through that, we see we have for each row, go through a single row, we're going to have the single division to get the elimination factor. Then we're going to go through all of the elements in that row. So we're going to have approximately, if we think about the number of elements in the row is going to decrease as we move through the pivots, let's call it n over 2 multiplications, and that would be this multiplication. We'll have n over 2 of this multiplication for each row, plus, and here's our subtraction at each element of the row. And again, since the number of columns is going to decrease from n at the first pivot down to 1 at the last pivot, we'll just say that it's n over 2. So we have n over 2 multiplications and then n over 2 subtractions. So overall, we're going to say that we have n operations. So this one division is kind of insignificant. So we'll say we have total of n flops for each row reduction. And then we're going to do that for each pivot element. So for each pivot element, we're going to have n flops down n minus 1 rows. Right? For that first pivot element, we're going to go down n minus 1 rows. And then we're going to do this for n minus 1 pivot elements. So if we just look at the leading term, we have n times n times n. And what we'll conclude is that overall, that the number of flops required to do this is on the order of n cubed. So what does that mean when we say it's on the order of n cubed? Well, it tells us that we can make a rough estimate that it will take n cubed flops to solve the system. So for the forward elimination step to solve the system. So a 10 by 10 system would take approximately 10 cubed equals 1,000 flops for the forward elimination step. Now, that's not particularly useful because the time it takes to execute a single flop depends on the specific computer, whether other processes are running simultaneously, and what else is going on in your code. But a more useful thing is to know that the computational cost will increase with the cube of the system size. So we know that a 100 by 100 system will take approximately 1,000 times longer to compute than a 10 by 10 system. And the way that we can see that is a 100 by 100 system, if we're scaling up by a factor of 10, so 10 more, so a 10 times larger system means 10 cubed, so there's where that n cubed comes in, more flops or more computational cost. So this is really useful information because it tells us how much longer we can expect the algorithm to take relative to a smaller system we can apply the method to for testing and debugging. So a common practice in scientific computing might be to apply our whole algorithm to a 10 by 10 system, debug it, make sure everything's working well, and then the real problem we're trying to solve has, say, 1,000 equations with 1,000 unknowns. But that's just too unwieldy for our debugging. But knowing this operation count can tell us how much longer or how much more computational cost that larger system would take. So this has all been focused on the forward elimination step so far. Let's look at back substitution. So for back substitution, I think the easiest is just to look at a 3 by 3 system here and see if we can extrapolate some conclusions about that. So if we look at the 3 by 3 system and go through, let's take this middle case x2 to be our average case. And we see in that average case we have one multiplication plus one subtraction plus one division. Right? So here's our multiplication, here's our subtraction, and then our division. So roughly, average case, we have approximately n flops per row. and then we're going to go down or up, since this is back substitution. You can say we're going to go up n rows. So n flops per row, up n rows is going to give us n times n, or order n squared for back substitution. And note, where this becomes significant, these operation counts is for large systems that are going to take significant computational time, and for large systems, n cubed is significantly greater than n squared. For example, 100 cubed is 100 times greater than 100 squared. So our main conclusion then is that the computational cost of Gauss elimination is on the order of n cubed, and that's all concentrated in that forward elimination step. The back substitution step, the cost is on the order of n squared, and as we get into systems that are large enough where the computational cost matters, that n squared cost is roughly negligible. And we'll take advantage of this to look at some possible improvements for certain applications of linear systems in the next video.